Oh, okay. Good morning. Happy Monday.
Good morning.
Let's see. I don't think. Oh, wait. I had the notes published late without the recorded lectures. I recorded those this morning, and by the end of the day, I'll have them posted online. They're up on YouTube already. I just have to put the link in the discussion page. And other than that, we are getting to be done with the models of computation section. Hold on here. There we go.
Professor Garfield?
Yes.
I had a quick question on homework 5. For the language that's the nested parentheses, is it just the nested parentheses? Because I was looking at I was looking at the homework. I thought maybe it was a different one. I just want to make sure.
Right. Yeah, and I think either in the samples or the homework, it wasn't just nested parentheses, it was an expression language, a simple expression language. And I thought I had just talked about nested parentheses because I had seen that actually in the practice problems, and I got confused between practice problems and the homework. Okay, let's see here. Okay, so we started out models of computation with the simplest ones, the finite state machines. We went into stack machines. We're doing Turing machines. And now after this, next week, we'll go into compilation. So it's a much more practical world, whereas the first few weeks were a theoretical world. But what I'll do in the computation is I'm going to tie the languages and grammar section into models of computation, because how does a compiler know that you've created a good line of code? Well, that's a string, and basically it answers the question, is that string language, the programming language that you're dealing with? And they use the Backus-Naur form rules directly to answer that question. So that's where we're going to go then, and then I think we've got 3 weeks of that, and then we go back into theory with lambda calculus, which is going to come and discuss. It discusses computability, but from a mathematical perspective, as opposed to Alan Turing came from more from a machine perspective. We won't focus on that aspects. We'll just focus on the form of lambda calculus. And the reason is it helps you, again, get another formalism under your belt that you may be able to use in the future, but in more immediate practical terms, from there we're going to jump into functional programming, and functional programming and lambda calculus are identical. So you're really learning functional programming thought and syntax as we go through that section. Okay, let's see. Models of computation, outcomes, and let's talk about Turing machine. You've all heard of Turing machine, almost certainly, because it's such a common term. And again, for the finite state machine and for the stack machine, if you look at the first couple of slides, the first one said, what's the theoretical value of studying this? And the second one said, what's the practical value of this, of studying this? And so I'm doing the same thing here. And Turing machines have theoretical value because all along we've been asking, what can a computer compute? And finally, we have a machine strong enough to actually do computation, and we can answer that question. So the Turing machines are ugly and inefficient in terms of how they represent things, but we finally have something that can perform computation, not just recognize languages. Practical value, virtually none, right? So these are theoretical devices. No real world Turing machines exist, except, some people have created one just because. I said for fun, which may be a generous term, out of boredom or nerdiness or something, people have created or programmed, I should say, Turing machines. But in the real world, no one is saying like a traffic light is a finite state machine. That's a real good comparison. It actually holds water. A soda machine is a finite state machine. That's also great. You can't find the equivalent of a Turing machine in the real world. So it's really a theoretical issue. But the results of the Turing machine have practical value. So what the Turing machine allows us to do is determine the limits of computability. And if your job is to create software, that's probably an interesting question for you, because you probably don't want to try to take on a job that is not computable. You probably don't want to try to solve a problem that is not computable. You know, your company gets a bad reputation because you didn't finish the contract and nobody hires you anymore and all that stuff. They can act as language recognizers. Now, this goes in keeping with the Turing machine has more power than a stack machine, which has more power than a finite state machine. Well, if it has more power, it should be able to do the things that those things did. So since we were treating the stack machine and the finite state machine as language recognizers, the Turing machine can do that too. That's not its big claim to fame, though. It can actually perform the computations, and quite frankly, it simulates programmable computers. So not only can it perform computations, we can program it in theory if we wanted to, but we would never do that because it's annoying. The main point, though, is there's the correlation between a programmable computer, like what's sitting right in front of you, and the Turing machine. Remember, this was all developed in the 1930s. And computing machines, the way we understand them today, started to be developed in the mid-1940s and really took off in the late 40s. So basically what Turing was asking was, gosh, if we ever do invent a computer, what can it do? And Alonzo Church was working on the lambda calculus at the same time, trying to answer a similar question. Turing and Church came to the same conclusion, that there are such things as non-computable problems, non-trivial non-computable problems, and developed the characteristics of them, and it's called the Church-Turing thesis. And it's pretty vague. It just basically says there are such things as non-computable problems. The result of that from the Turing machine formulation makes more intuitive sense to us when we're talking about computers, because a Turing machine's correspondence or similarity to a real-world computer is pretty obvious, and so it's an easy transition to make. It's a little harder to make that transition from the heavily dense mathematical notation of lambda calculus, because he was asking a slightly different question. Okay, so we're going to get there in basically a lecture and a half, or 2 lectures, which means it's a top-down. We're just brushing the surface here of Turing machines so that you have an understanding of what they are, how they operate, and what their importance is in the computer science community. Again, you can have an entire course based on these 3 modules. In fact, you can have multiple courses based on these 3 modules. And if you did, you would take a deep dive into Turing machines and go through a lot more rigorous proofs about what they do and what they don't do. I kind of went through the high-level, trust me, it works kind of proof. Okay, just to review, we are finally at type 0, the unrestricted languages. Now, I'm not going to differentiate between type 1 and type 0 here. And here's why. They both deal with Turing machines, one with finite tape, one with infinite tape. And we're just going to deal with the infinite tape. So we're skipping over context-sensitive languages and dealing with the unrestricted languages. And again, in order to really demonstrate why putting a finite tape on a Turing machine actually changes the category of the language that you can deal with, is a nice 3-week-long process in a class that we do. So let's just skip over that. Okay, very informal definition. What are these things? Again, you've probably heard the term. So it's hard to be in a college computer science minor, major, software engineering minor, major, and not even hear the term. It's a finite state machine, instead of being coupled though with a stack, it's coupled with a tape. And the tape you can think of as having cells on it, and in each cell you can write a single symbol. And then you have the ability to move that tape back and forth, left and right, left and right. So think about what's changing here. With the stack machine, you could put a whole bunch of data on the stack, but you only had access to one element at a time, being the topmost element. And if you wanted to get access to elements lower down, you had to destroy the stack. With the Turing machine, you have access to any of the elements on the tape, and you don't have to destroy the tape or destroy the other symbols on the tape. So you can move, if you think of it like an array, you can move to a position in the array. This effectively simulates random access memory. Now, the way random access memory works in your real-world computer is far more efficient, because you name a memory address, the machine immediately goes to that memory address. It doesn't start at 0 and count up. Whereas here on the tape, you start at the left end of the tape, and then you can move only one space to the right, one space to the right. So once you're in any particular spot, you do have to continually jump to the left, jump to the left, jump to the left, or to the right, one cell at a time. So in terms of the speed of memory access, there's a difference. In terms of the effect of what that means, there's none, because you still have access to all of the memory at any point in time. In order for that memory to work, you have a read-write head, so the head can look at a symbol, acknowledge the symbol, and then can write something on top of that symbol and erase it. So not only do we have random access memory, we have read-write memory. It's exactly what your computer has. In addition to the finite states that we're used to dealing with the finite state machine and stack machine, we have 3 special final states that are called halt, yes, and no. And those are the only final states: halt, yes, and no. The 3 states are used this way. If I ask a decision question is, hey, should I do this? Yes or no? Or is this string in the language? Yes or no? Right? So any kind of a question that's a yes, no answer is a decision question. So if you're asking a decision question of the Turing machine, it will halt either in yes or no. The other one, this generic halt, is just sometimes the result of the computation the Turing machine does is just what's on the tape, which is, again, similar to how your real-world computers work, right? Where is the result of your computation? It's whatever's stored in memory when your program's done. That's the result of the computation. So that's just a generic halt, and then whatever's on the tape is the answer. There's no math model for let's go look at the tape. Okay. Instead of an input alphabet, now we have a tape alphabet, because that's what both the input and the output is about. So instead of receiving strings and processing strings that are composed of some alphabet, we'll have an alphabet by which we can read and write symbols onto the tape. And again, we need some special symbols added to that. And the special symbols are, it's an infinite tape. And not only is it an infinite tape, it's a two-way infinite tape. Now, it doesn't have to be, but you generally consider it a two-way infinite tape. So if I'm at some point, I can go infinitely far to the left or to the right. Well, that doesn't mean you're interested in the whole tape at any point in time. Usually, there's just a section of tape that you're interested in. So you have to bound that. Well, on the left-hand side, that gets bounded by a special marker, and I'm going to use delta. Most authors, or some authors, the one that I'm going to show you the notes for in a minute, have a triangle that's on its side. And I spent like 20 minutes trying to find a triangle on its side or create one in PowerPoint, no dice, so delta's close enough. And on the right, it's this square cup image. And the rules are, on the left, you cannot change that. So we can't expand the string to the left, and we cannot move the tape head past that leftmost marker. But on the right, you can change it. So if over time, as you're doing a computation, you might need to make your string get bigger and bigger and bigger as part of the computation. And you can do that because that rightmost symbol, that big square cup, you can just keep moving it to the right and moving it to the right and moving it to the right. I mean, you literally can erase it from the tape and rewrite it someplace else. So that's how things go. Now, you might ask the question, well, wait a minute, why can't we go to the left? Are we restricting ourselves? And the answer is no, because you still have access to an infinite amount of tape. And so you haven't restricted the machine. The transition function is much like you'd expect. Basically, you look what state you're in and you look at what's on the tape and then you do something. And there's only a few things you can do. Number one, you can change state. Number two, you can write something onto the tape. And number three, you can move to the next cell, either to the left or to the right. So our state transitions are going to include the left arrow, right arrow, and the dash mark, meaning don't move. So that's an informal discussion of what the machine is about. Are there questions yet? Okay, let me make a slight note here. Let's show a correlation between the language and the grammar and this notion of how we can make the rightmost side of the tape change. If I wanted to make my string bigger, I can, and I would move that right big, I'm calling it big square cup. I'm moving big square cup to the right. If I want to make my string smaller, I can, I move big square cup to the left. This is completely in keeping what we said an unrestricted language can do. An unrestricted language can remove terminal symbols from the string. So your strings that you're processing in an unrestricted language can grow and shrink and grow and shrink. And then we have a mechanism to account for that in the Turing machine. So again, there's a correlation. Okay, more formal definition. Notice now we have a 1, 2, 3, a 4 tuple. You'd think you'd have more, right? A finite state machine was a 5 tuple. Stack machine was a 7 tuple. Oh my God, a Turing machine's got to be so much more. It's actually less. It's only the set of states. And we're going to include in that set of states halt, yes, and no. It's the alphabet, which is now the tape alphabet, when we're going to include triangle, big square cup. We do need to specify an initial state Q naught, and then we have the transition function delta. Notice there's no final states. We removed that, no set of final states. And the reason is that that role was taken up with halt, yes, no. So there's no need to have a except by final state. I've put some notes up from Cornell. And let me show these. Do I want to show these now? Yeah, I want to show these now. Let me show these now. This is, I don't know who wrote this, but I've never, in my mind, seen a more concise and clear description of Turing machines and their operations. I'm going to qualify that statement in a little bit. So I put this up here for you. You'll note it's 21 pages big. I'm only asking you to go through the first 3 pages. We do Turing machine, blah, 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 some examples of Turing machine. And then right here where it says 2.1 pseudocode for Turing machines, you don't even need to read that. You don't need to go past that. Now you can if you want to. I'm going to talk about universal Turing machines. And what do you know? There's universal Turing machines. So this person does go through the process. So instead of those notes that are similar to this that I made some other modules, I'm using this. I don't know that I could do it better. The only thing that would change is the notation. So let me talk about some notation issues here. I don't know why. This author uses K for the set of finite states instead of Q. Most people either use capital Q or capital S. And Cornell likes K. And then the special start state, instead of Q naught, they use S. And that's not too crazy. A lot of people use S for their states. So that's the starting state. Other than that, we are the same. We have the alphabet sigma, and we have the function delta. Right? So other than that, it's the same. So there are some notational differences. Other than those notational differences, there are some things that are expressed here that may be confusing. And so I'm going to ask you not to worry about these things. For example, the delta function is expressed here as K cross sigma. And then this big long thing here, oh, K union halt cross sigma cross left, right stay the same. And all they're saying there is this: the delta function takes as input a state and a symbol. K cross symbol is the way we say all combinations of states and symbols. And what does it output? It outputs a state, a symbol, and a move left or right, or stay put. And that's what this is saying. It puts a state, cross, symbol, cross, move left or right. This is just the formal way to write that. And those crosses mean that that's all possible combinations of state, symbol, and move left or right, or stay the same. So you might see that, you know, there's a little bit of notational denseness here in the writing, but it's because, again, they're going to go on and do a lot of formal proofs with this that we're not going to touch. What I really like about this is the examples. To go through these examples. So really, this is the heart and soul, and I've got these copied on our sheets. They give 3 examples, I'm giving 2. So anyway, just be aware it's a good set of notes. They're there for you. And be aware, you know, notational differences. After a little bit, those notational differences disappear for you. You get used to them. Okay, before we go into the examples, I'm pausing for questions. Okay. I think I did these in reverse order. So that's what came out of the Cornell notes. Let's talk more informally, first of all. And this is the level that I'm looking for the homework questions. And the homework will just be, I'm going to say, here's 2 different things, you know, describe this Turing machine that would achieve these things. So only 2 problems. So let's use the Turing machine as a language recognizer first. And we'll let sigma be 0, 1, and you know, left-hand side, right-hand side. And we're going to recognize strings that represent a correct addition equation. And we would do that by, again, this is highly inefficient, but it's a way to do it. 0, 0, 0, 1. So I'm representing the numbers as the numbers that I want to add together as zeros. Like that's the number 3, and then a 1, and then 0, 0. That's the number 2. So I'm literally representing the number that I want by how many zeros I put down, you know, how many hash marks I put down. It's the old method of, you know, this is primitive math, right? How many goats do I have? Well, I have a bucket of pebbles, and every time a goat goes through the gate, I throw a pebble in the bucket. That's how many goats I have. All right, so this would represent 3 plus 2 is 5. This represents 3 plus 0, because the ones are together, equals 3. And this is 4 plus 3 is 7. Notice this is not a notational scheme you would want to adopt. But that is a way of encoding correct addition equations. And if that's our language, then we should be able to recognize those. And the Turing machine can rather easily. I'm going to start over at the left-hand side, and I'm going to traverse to the right until that first 1 is encountered. And then I'm going to remove that 1. And I'm either going to leave that cell blank, or I'm going to shift everybody to the left. We'll talk about how you can shift in a second, because that's what the author's first example is. The Cornell notes first example is. So anyway, I'm going to remove that 1. Now I've got all the zeros together. So instead of, let me see, what do I do? If I did that here, instead of having, I can do it this way. I would have that. And I've reduced the question now to, are the zeros on the left of that 1 the same number as the zeros on the right of that 1? And what I would do then is traverse all the way to the left till I get to the start state, go 1 step to the right, and if there's a 0 there, I'll delete it. And then I'll keep traversing to the right until I see the 1. And then if there's a 0 next, I'll delete it. And then I'll go back to the start state. I'll see a 0, I'll delete it. Go back to the 1, delete it. So what I'm doing is I'm going left and back along the states and along the string. And what I'm doing is I'm transitioning into states. So right now I'm at the state where I've seen the beginning of the marker. I would transition to the state where I'm going to go and look for a 0. I found the 0. Now I'm transitioning to the state where I'm looking for a 1. I found the 1. So I transition to the state where I remove a 0, transition to the state where I'm going to go left again. And you can see, I can just keep doing this back and forth until finally I'm in the state where I'm looking for a 0 and I got a 1. So I'll just check to make sure there's no zeros after the 1. And if that happened to be true, then I can say, yes, this string is in the language. Gosh darn it. How does it help you to get even zeros on both sides? So 4 plus 3, look at the equation. 4 plus 3 is equal to 7. Is 7 equal to 7? So if I'm demonstrating that a number is the number of zeros that I wrote down, I should have 7 zeros equals 7 zeros. Is really what I want here. So all I do is I get rid of if I have 4 plus 3, that's 4 zeros, a 1, and 3 zeros. So they're separated by a 1. So I get rid of that 1. And then I'm going to check to see if I have 7 zeros and 7 zeros. If I do, it must be a correct addition equation. I love how Zoom puts up the chat notice and then hides it from me, so I can't. Okay. So that's a verification of addition, but it's not addition. Doing addition is actually much easier than that. If I'm going to keep this same horrible notational scheme where I represent a number by the however many zeros I laid out in a row, then I can actually perform that computation of addition in a much easier way. Here would be how I'm asking the question, what's 1 plus 4? And here is what's 3 plus 0. Here is what's 2 plus 2. And if the answer is represented by how many zeros in a row I have, all I have to do is go through and delete that 1. And that's just a freakish thing with addition. But that's pretty easy. I start at the leftmost string. All right, I start at the marker on the left part of the string. I keep traversing until I find a 1. I delete it and I shift everybody to the left. We'll talk about how that can happen in a second. And there's my answer, halt. Notice now the answer is not yes or no now, it's halt, and the answer is whatever's on the tape. Whereas before, I was going to check to make sure that I got, I better fix this. Before, I was going to make sure that I had that when I was done, and then I would say yes or no. Here, I'm just saying halt. And the answer is whatever's left on the tape. So we can perform calculations now instead of just recognizing things. And again, that's a way to go. Now, this is a horrible notational scheme. What if we actually wanted to use binary numbers, zeros and ones? And that's what the author does. He jumps right into binary math. You have to do, they do some cute tricks. You have to convince yourself that it works, okay, for some of this stuff. So let's go to the author's first example. Now here, instead of just talking notionally about what the machine's doing in machine operations, they actually lay out the proper transition function. They actually lay out what this machine looks like. Now here, you don't really care about drawing the machine state circles like we did with the finite state machines and the stack machines. You can do everything just with the table. It does make it a little harder to visualize and to construct these things. And that's one reason, and for this semester, I'm not going to worry about having you guys make the table. In the past, I have had students do that, but we also spent a little more time than we're going to spend on finite state machines. So the trick with reading these examples, ask what they want to do. For example, let's construct a Turing machine that takes a binary string and appends a 0 to the left side of the string. He should say prepend, actually, I guess, and I think he does in the next thing. And then he says, oh, well, here, he's already got the solution here. He or she, I don't know who wrote this, or they. The notes already puts the solution out there, as if it was so obvious to everybody. Well, it's not so obvious to everybody, especially when it's your first example. But what's good is this description of what's happening down here. That's what's good. So what's happening is, how can I do this? No. There it is. What's happening is if we had the, I'm gonna have to do left-hand side because I don't want to do the triangles here. If we have a binary number like 1101, and then we have the right-hand marker, my computer helps me all the time. So what they're saying is, look, all you have to do is start at the left-hand side and you go and look at what the first thing is, and you don't care what the first integer, you don't care if it's a 0 or a 1 so much. You know you're going to put a 0 there. So you're going to take that thing and you're going to put a 0 there. But you have to remember that you just saw a 1, which means now you go to the right, remembering that you're about to write a 1, and you overwrite this guy with a 1. And now you remember, okay, I just saw a 1. What you're doing is you're copying the string 1 by shifting it 1 to the right. Okay, now I saw a 0, but I just saw a 1, so I have to put a 1 down. Wait a minute, that last thing was a 0, so I'm going to put a 0 down, but now I have to still move to the right. Okay, that last thing was a 0, so it's a 0. That last thing was a 1, so it's a 1. And now I put a 1 in there, and I move the right-hand side marker over 1. And then once I've done that, once I'm at the right-hand side marker I know that I'm at the end of the string, and I've rewritten the right-hand side marker, the big square cup, 1 to the right. All I have to do now, technically you could halt there if you wanted to. I'm going to go all the way to the left, 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 and I'm not going to do a thing. I'm not changing anything. Left, 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 till I get to the beginning, and then I'm going to halt. And if you read what's happening here inside this delta function, that's what's happening. And they use fairly good mnemonics. So they start in the start state with the leftmost symbol, and they know they're going to move to the right and write a 0. That's what state R0 means, and that's a mnemonic for that. I'm moving to the right and I have to write a 0. So what do? They're going to go to state R0. They're going to make sure the start symbol stays put, then they move to the right. Now they're at R0, and if they see a 0, now in my case, let's see what happened. Let's do that string. The way I originally formed that string was that way. So they're in R0, and they see a 1. That's the first symbol, R0, 1. That tells them to go to state R1, meaning I'm still moving to the right, and I know I have to put a 1 down next. You're in R0, so they're going to transition to R1. You're in R0, so that's why you put a 0 down, and you still move to the right. So what happened? As a result of that, that 1 got replaced by a 0, and now here I am. I need to space these out. And now here I am in R1 looking at a 1. So what does R1 say to do? Stay in R1, put a 1 there, go to the right. Put a 1 there, go to the right. Now I'm looking at a 0. I'm in R1, 0. What does it say to do? Now you go back to R0, put a 1 there, keep going to the right. So this 0 gets replaced by a 1. If you keep walking through that, you end up doing this until you go to the right-hand side, the big square cup. And what happens there? Well, if you're in R0 and you see big square cup, now transition to the state where you're traversing to the left and put a 0 there and start moving left. If you're in state R1 and you see the big square cup, put a 1 there, go to the state where you're transitioning to the left and start moving left. I'm not thrilled with the fact that they didn't put an end of string marker back on the right-hand side, but that's okay. Now, there's got to be questions. If you think of it intuitively, you can convince yourself it's a legitimate scheme. Convincing yourself that that table represents that intuitive scheme can take a little bit of time. What is the point of their machine? They're simply showing that you can add a 0 to the front of a string. Now, why would they do that? Number one, it's a simple example. Number two, if I can add a 0 to the front of a machine, would you also believe that I could add a 1 to the front of the machine? Would you buy that? I would buy it. There's nothing magical about 0 or 1. So if I wanted to, I could take a string and I could add a 1 to the front of it if I wanted to. Yeah, they're showing that that is a computable problem because we built a Turing machine to do it. So it's a computable problem, which shouldn't shock us, right? If we can't add a 0 to the front of a string, not much is computable. So that's all they're showing is they can add a 0 to the front of the string. Now, it wouldn't have bothered me if they did this writing a 1 in front of the string, but I think they wanted to kind of disguise what they were doing. Here's why they're doing that. The very next example that they're showing is to do binary addition, adding 1 to a binary number. Not binary addition per se, but adding 1 to a binary number. If I add 1 to a binary number, let's get my friend Notepad up. Here's a number, 1001010. Now, if I wanted to add 1 to that, wouldn't I get 100010011? Is that true? You buy that?
Yeah, that's right.
I would buy that. Well, because I'm gullible, I would buy that. Okay, so what if this was my number, 111? What's the binary addition to that? 1000, isn't it?
Yes.
So if you're going to add 1 to a binary number, there are times when you actually have to add a brand new digit at the front of the number. Now, you may ask yourself, is it possible? Could I possibly add a digit to the front of a string of 1s and 0s? And we just did that. So he's kind of setting you up for the +1 problem. He or she, or they. So that's what's going on there. They're setting you up for the +1 problem. Let's talk about the +1 problem for a minute. I think I want to put these on the same. No, I don't. I want to do it like this. So they're working their way up to binary addition, actually binary +1. We can get to binary addition. Okay. What about 1111? Wouldn't that be 111100101? What about 111001? Wouldn't that be 111010? I'm going to start a pattern here. See if you can find the pattern. 110011 becomes 110100. 110111 becomes 110. Whoops. That can't be right. Right? What's the pattern? Forget that you're adding numbers. Do you just notice a pattern in those strings, those pairs of strings? I got to get there before it disappears. 0 followed by 1s, 1 followed by 0s. Right. So what specifically happened? One of the 0s got changed to a 1, right? So one of the 0s in this string, say, got changed to a 1. Which 0 got changed to a 1? It's always the last 0 on the right. Did you notice that? And then what happens? All the ones on the right of that got changed to a 0. So if I said, you know how you do binary addition? You go find the last 0 on the right, in this case it's this one, and you turn it to a 1. And if there's any ones further to the right, those get turned into a 0. That's true here. It's true here. I found the last 0 on the right, I turned it into a 1, and then the one that was to the right of that got changed to a 0. It works with 2 ones. I take the last 0 to the right, I turn it into a 1, and all the ones behind it or to the right of it got turned into a 0. And you knew this because you already told me that is equal to that. So what you're doing is if you look at these strings, basically all you have to do is ignore the first 3 and just look at that, right? The last 0 on the right becomes, make that more obvious. There we go. So that's the trick. You take the last 0 on the right and turn it into a 1, and any one that's further to the right gets turned into a 0. And if you do that, you're doing the add 1 function on a binary string. Now the problem is, if my string is all 1s, I can't quite do that. The first thing I have to do is shift them to the right and put a 1 in front of them, and shift them to the right, and then change them all to 0s. That's almost like the overflow condition, right? And so the machine that comes up next is, as long as the size of the number doesn't have to change because of the +1 operation, we're going to find the last 0 on the right, turn it to a 1, and then all the ones behind it turn into a 0. But if the string happens to be made up of all 1s, like this one is, if it happens to be made up of all 1s, we're not going to find any 0s. We're going to find an end of string marker instead. We're going to find the right-hand marker instead. So now what do? Oh, let's go all the way back to the front and do the trick that we learned in the first example of adding something to the front of a string. So I'll add a 1 to the front of the string, and then I'll traverse to the right, and I'll just keep turning all those 1s into 0, 0, 0, 0, 0, 0, 0. Do you believe the math of that works? You have to convince yourself that that cheap trick works in terms of being mathematically correct. And it is. If you don't buy it, do like I just did. You know, maybe. You never know when the aha moment's coming, right? Do 10 of them, do 100 of them, whatever. So that's what's happening for the second one. So the first one was a setup. The first example was a little bit of a setup for this one. The first example was saying, can we prepend a 0 in front of a string? Yes, we can. Now we're going to do the same. Now we have to use that here. We can prepend a 1 instead of a 0 in front of the string. Oh, and by the way, instead of just copying the string and shifting it to the right, we're going to switch all those 1s to 0. So it is easy to see that the following rule, yeah, really easy. You have to do what I just did, right? Play around with adding 1 to a bunch of digital integers and convince yourself that it really is work. Easy to see the following rules does n+1. Find the rightmost occurrence of the digit 0, change it to a 1, and every digit to the right of it goes from a 1 to a 0. If you're not convinced of that, you know, find me a counterexample. Find me a situation where that's not true. And then the only exception is if the binary representation does not contain a digit, it's all 1s. Then what you have to do is slap a 1 in the front and then change all those 1s to a 0. And that's what, if you go through this machine, go through this state machine here, that's what it's doing. And what they're doing is saying, look, if you go through here and you actually found where are we at here? I want to get to where I get to state T. If I go all the way to the right, and now I'm changing. I'm looking for that last 0. If I find a 0, oh yeah, how do you find the last 0? How do you find the rightmost 0? If I'm going from left to right, I'm going along, along, along. I find a 0. How do I know it's the leftmost 0? Or I'm sorry, the rightmost 0? You really don't, right? You don't know. The way you have to find out what the rightmost 0 is go all the way to the end of string, find that right-hand side marker, that big square cup, and then go to the left and look for your first 0. If you're going left and you find your first 0, isn't that by definition the last 0 you would have countered while you're moving to the right?
Yes, since you're
Yeah, see, so
would have been the last
okay,
zero.
so that's what happens. They go, I believe, I better check the machine. You should go all the way to the right, then start traversing to the left, and as soon as you hit that 0, now you know you're good. So here, we're saying R0, keep moving to the right, don't touch anything, keep that 0 there, keep going. R1, right, keep going, don't touch anything. If you hit the end of file marker, now keep going to the left, keep that end of file and end of string marker there and go to the left. Now if I find a 0, I go to this state T, and the state T is basically saying, it's a normal string. It's got at least 1 0 in it. So I can just do my cheap trick of turning that 0 to a 1 and then going to the right. Actually, what do? If they find a 0, they turn it to a 1. If they find a 1, they turn it to a 0. So they've already turned all those 1s to a 0. And you go to this state T, which says, okay, I found at least 1 0, so I know I'm good. I'm going to turn that 0 to a 1, and then I'm going to keep going to the left. And where did I go? I turn that 0 to a 1 up there. And then everything else that I'm doing is I'm just going to go to the left till I find the beginning of the string, and then I'm going to halt and say I'm good. Walk through this table if you want to make sure that it makes sense. But that table is giving you the instructions that are described in this paragraph down here. Let me think how to say this. There are 2 things at work here. One is, did it solve the problem? And 2 is, what does this symbology mean over here? Those are actually 2 separate problems, and I would advise you to keep them separate. One is, you can follow what the machine is doing through this transition table without knowing what it's doing. Does that make sense? You can actually perform the actions without knowing what the intent is. That has to be true, because that's what computers do. That's what computation really is. Then the separate question is, did it really add 1 to the string like it was supposed to? That's a separate question, and that goes more into the logic of what's happening here. Now, when I'm asking you guys, I'm going to ask you to say, okay, tell me how you could build a finite state machine to do such and I'm sorry, a Turing machine to do such and such. What I'm asking you is, give me the logic of how it would work. You don't have to build this table out. Just tell me in general terms. Oh, I'd start at the left, I'd move to the right till I find this, then I would do this, and I'd move to the left till I found that, then I would do that. That kind of sequencing is fine. If you want to put everything in tabular form, that's fine too. But I would still ask for a natural language description of what the heck you're trying to do. Okay. We'll continue with these examples on Wednesday because they do bear repetition and you need some time to absorb this stuff. I have videos ready that I'll post this afternoon also that basically repeats all these, and you have access to all the notes. So then on Wednesday, we'll go through this and then talk about what it means in terms of computability. And then on Friday, if we need to, we'll keep doing this or we'll have office hours. Okay. Thanks for being here, everybody.